All right, so now I want to start dealing with rotational motion of objects. So far in this class, we've only dealt with linear motion of objects. In other words, moving left, right, up, down at an angle, but the entire object isn't turning at all. It's just all moving in the same direction together. But now I want to deal with what about if objects rotate? You know, so like over here, maybe this is a fishing pole, right, around a pivot point here or someone's hand, and if a fish pulls down on it, the pole naturally rotates that way, or wheels naturally turn, rotate. Now we've done centripetal force, which is rotational motion, but now I need to talk about forces that cause that on the outside and dealing more in depth with rotational motion. To begin that idea, we need to talk about torque here. Torque, if you will, is the measurement of, and this is kind of a, not a great definition, but it's one that might help understanding, measurement of the turning force that causes an object to, key thing here, it's causing the object to rotate. So torque is, if you will, what causes things to rotate. It's not a force, although force is definitely part of it. It's force times the distance between the pivot point and the where it's being applied, the radius, if you will, but we'll get to that. Mathematically speaking, it is the cross product between the length of the rotation arm, or the distance from the pivot point to where the force is being applied. So the length of the rotation arm and the force applied that's causing the rotation. And that's what this equation is right here. Torque, use Greek letter tau, is radius. This awfully looks like your old school times symbol from back in elementary school, right? There's a reason that as you get into high school, you don't see this x being used, and it's not just for algebra reasons that we use the variable x. You don't see this being used as multiplication anymore, because mathematically that stands for cross product, which is a three-dimensional, it's a three-dimensional vector idea here, because I have a vector of radius and I have a vector force, right? And then in 3D, using matrices, I actually take the cross product of it. Now, I'm not going to be teaching you in this class how to deal with the cross product. That's not the goal here. But if we were just looking for the magnitude, or in other words, just the number, not the direction for torque, for tau. So this is going to give me the direction also. But if I'm just looking for the number or the magnitude, I can use this equation right here. So this is the equation that you're going to need here. Torque equals the radius times the force times sine the angle. So now check this out over here. What I said was a fishing pole. So I have some fishing pole, radius r, and someone's holding it over here at the end. So this would be my pivot point. And I guess I should define that pivot point which an object rotates around. That's kind of common vernacular though. So I have my pivot point here, and I apply a force down on this pole, fishing pole, whatever it is, something's pushing on it here at some angle theta. This is going to cause a torque, which will cause the thing to rotate, right? Rotate downwards this way. Now let me actually zoom in on this to where I can kind of give an idea of why this sine theta is important here. My sine theta actually comes from needing the perpendicular component. This is all about trying to get the, if you will, remember this symbol, perpendicular component here. So check this out. If this is my angle measured between the radius, or the distance the force is being applied, so here's my radius, right? The radius and the force being applied. The angle is between the two. So I'm looking for the perpendicular component. So let me draw in a nice little right triangle here, right? I'm looking for the perpendicular component of it, which means the y-axis right there. And if this was turned vertical, it would be the x-axis. But sine theta is opposite over hypotenuse, where the force is the hypotenuse of my triangle. So that's why sine theta, because I'm looking for the perpendicular component of it. So check out my perpendicular component to the radius right there. So that's why sine theta. If you were given an angle measured relative to the normal, right, something along maybe this line right here, theta, you would need to do 90 minus that to use sine theta, or you could use cosine there if need be, but you need to use 90 minus that to get back to our angle theta. All right, so once again, torque is your radius, or how far away from the pivot point the force is being applied, times the amount of force, F, being applied, times sine of the angle, right, between the radius and the force. That will give you the magnitude of torque. The purpose of the sine is to get the perpendicular component of the force that's pushing straight down on it. Because forces that push straight out or straight in on your on whatever is trying to rotate doesn't cause rotation. I mean, think about if you were just to push the pole straight in like that right here. Well, that's not going to cause the pole to rotate. That's going to cause the pole, from our perspective, to slide to our left, right, in linear motion. So there is no torque associated with that. That would just be a sum of the forces problem, not what we're dealing with in this unit. Units for torque is newtons times meters. Which happens to be the unit that, if you put them together, if you remember impulse, works out to be the joules, same thing as energy. Here, though, you can't combine the two. You need to leave them separate, newtons times meters, because it doesn't work out to be, because torque's unit isn't a joule. Remember, energy is a scalar, right? Thus, the unit's joules doesn't really have any direction associated with it. It's a scalar. Vector, on the other hand, torque, on the other hand, is a vector. So we need to leave it newtons times meters to differentiate between joules, which is a unit, as a scalar unit, and torque, which, newtons times meters, a vector unit. Okay. So here again, just trying to highlight radius, force, angle between the two, right? RF sine theta. If my theta was 90 degrees, if it was perfectly straight down, remember sine of 90 is 1, so it would just be the radius times the force. This also can be done with anything that is in a circle, like a wheel or something. You have a radius from, let's assume the pivot point's in the center. It doesn't have to be, but let's assume the pivot point's there in the center. I have a radius out to the outside. I apply a force on that, right, which is going to cause the wheel to turn. Some angle between the two. It looks like I have here, it's set up to be 90 degrees. And that's going to give me a torque on that, which will cause the object to rotate. So let me work a basic example problem for you. I have a bolt that requires a minimum of 350 Newton meters, our unit for torque, right? Newton meters of torque to turn. So I need to turn this bolt to loosen up whatever it is, right? It's in a position, though, whether it's back behind something or it's tucked away in a corner, where at best you're going to make a 75-degree angle between the person's hand trying to apply the force, right, and the wrench. How long of a wrench must be used? If a person at best can exert in that position 320 newtons of force? So I have some wrench here, right? And pardon the terrible drawing, but that doesn't matter. Here's my pivot point, right? This is the point that I'm going to turn around. I'm looking for R, and I'm applying some force down, maybe like this, F, that can make at best a 75-degree angle. And I do know the force, right? The best force I can use is 320. So with torque, the longer the radius, if you look at the equation, right, F, let's tau equals, and let's actually make that R here, RF sine theta. The longer the pivot point, or the longer away from the pivot point the force is applied, R, the bigger your wrench, if you will, the longer the distance, it's a multiplier to the force, in essence, in this equation. So a longer wrench is going to give me a greater torque, right? A longer R will give me a greater torque. So if you think about road construction and working on heavy machinery, there's a reason why they have wrenches that are insanely long. It's because those bolts are really big and require a whole bunch of torque to try to loosen up. In heavy machinery, those bolts have to be in there really tight. They have to be really large. So you're going to need a huge torque to loosen them, and the human body can only apply so much force, F. Well, if you use a really long wrench, R, you can apply a smaller amount of force and get a huge force because of your large radius here. So same thing with this problem. What is the smallest wrench I can use in this situation? So I have 350 Newton meters of torque equals, I'm solving for R. My force is 320 newtons. That's the best I can do, right? I'm trying to find minimum R. So I'm going to apply every bit of force I got to get R to be low. Sine of my angle, 75 degrees. And now it's just algebra. And with significant figures, I come out with 1.1 meters. So this has to be a relatively long wrench to actually make this bolt turn here, a 1.1 meter long wrench. Let me go back and emphasize something here. You've heard this idea of mechanical advantage, and I'll talk about this a little bit more in class, and we've talked about it briefly. But the idea, and this is another way of using mechanical advantage, it's really a shortcut for torque here, but the longer your radius, right, the less force you have to use to get the exact same amount of torque to turn something, right? If you have a very short radius or a very short wrench, in this case, you're going to have to apply a lot larger force to get the same torque or turning capacity. All right, so that's torque. I'll do a few demos and talk about this concept because it can be kind of confusing. Make sure to come in with questions whenever you come into class. And so I'll do another example problem for you, do a couple of demos, and check out the assignment below.